So let's have this diagram right here. So we have our 3D space right here. And well, let's consider this surface. And let me do some very generic surface right here. Nothing too crazy actually. Let me make this look like 3D. Alright, it's gonna go in the background. Well, so we have a surface given by some f of x, y. So this function f of x describes this surface right here. And well, so we want to find, we're going to go to some point. Whatever that point is, this very generic point. And what we did in the previous section is find the derivative with respect to x to find the rate of change in the x direction and the partial derivative of it with respect to y to get the rate of change in the y direction. Well, so this point right here, if we make some sort of a projection here, essentially it's going to give us this. And so what did we do again back in the previous chapter? So we did the rate of change or the slope in the x direction for the derivative with respect to x, and we also did it for in the direction of y for the partial derivative with respect to y. Alright, but well, again, what if we want to know the rate of change in a different direction other than just x or y? Well, so let's define this this sort of tangent, if you will. Well, so if we project this, I'm going to use a different color to project this line right here. It's going to look like this with some angle theta with respect to the x-axis. In this case, the x-axis will be this projection in here. So what are we going to do with this directional derivative? We are going to find the derivatives with respect to x and y, but then we are going to do some product to steer that rate, to steer that tangency in some direction, in a desired direction. And by the way, this vector that we have here should be a unit vector. So this is a unit vector. And for now, for the simplest case, let's consider that unit vector cosine theta I sine theta j. Well, so the directional derivative then will be the product, between those derivatives times cosine and times sine respectively. So essentially, those derivatives in the x and the y direction will be weighted in their corresponding x direction and y direction. Of course, this is not the only possibility for unit vectors. Recall that we define a unit vector u with a hat, which is u1 plus u2. Okay, so well, so let's see. So this will be our formula to find for now. Also, considering just changing the direction with some angle. Okay, so what is this derivative going to be? Well, it's going to be a scalar again, because we're finding the slope, we're finding a rate of change, so that should be a number, not another vector, because check this out. So essentially, we are using this vector, and another way to do this is partial f with respect to x times the unit vector, the component of the component u1 partial f with respect to y times the component u2. Come on. And well, if you look at this calculation here, this expression, doesn't that look like some dot product between two vectors? Well, we're going to define this couple of partial derivatives later as a vector. You will see how is this going to look like. Well, again, we do this because again we have infinitely many ways to go in a direction. So how about let's have a look at one example. So we have the surface given by z equals x squared plus 3y squared minus 5. Find the directional derivative of f at some given point, in this case the point 1, 3, in the direction of this vector u, which by the way it's a unit vector. Alright, it's important that it is a unit vector, otherwise, well, I'll tell you what happens in a minute. Alright, so number one, we need to find the partial derivatives, partial f with respect x. And in this case, the derivative with respect to x, what's the derivative? 2x. What about the partial with respect y? 6y. All right. So what are we going to do? We're going to find the directional derivative for the function xy in the direction of the unit vector u. I'm going to put a hat to denote that it's a unit vector. Well, so in this case, we're going to multiply the partial derivative with respect x times cosine of pi over 6 plus the partial derivative of the function with respect to y times sine of pi over 6. So, in this case, the partial derivative with respect to x will be 2x. What's cosine of pi over 6? Isn't that square root of 3 over 2 plus 6y root of 2. I mean, it's 1/2. What's going on? 1/2. And that's our derivative. Our directional derivative. So now we need to find this directional derivative at the point 1, 3. So in this case, just plug in 1 for x and 3. And this is going to give us root of 3. 6 times 3, which is 18. 18 divided by 2, so that's plus 9. Alright, so that's the directional derivative at that given point at 1, 3. Well, one thing you need to observe here is, let's look at the sign. Because in this case, we've got a positive number. Well, so what we're going to do, go to the point 1, 3 and on the surface, or along with the z component as well. So that means that if we start moving in the direction of this vector, in other words, the vector, let me write it down as a vector, root of 3 over 2, 1/2. This means that we're going to go uphill. And that's because the sign of the derivative is positive. So we're going to go uphill in the direction of this vector. All right. Let's look at the next example. So again,